This lecture is a big deal. It's the culmination of everything that we covered already. And we're going to walk through the life of a packet from the sender through to the receiver and how everything works together to make that possible. So really it's a review of what we covered already, but this is going to tie everything together and it's going to prove to you that you now know the fundamentals of IP networking. So in the example here, we've got host A on the left, and it's going to send some HTTP traffic to our web server over on the right, which is www.flakbox.com. It's going to use the FQDN to send that traffic, so it's also going to need to resolve that FQDN name to the IP address using DNS. Also, it's a routed network. We've got different IP subnets there, and we've got a couple of routers in the middle of the topology. I've deliberately included multiple subnets, routers, and a DNS server because I want it to mimic what you would see on a real-world network, because I want you to be confident that you can work on real-world networks and you understand how IP networking actually works. Because of that, there's quite a bit to this example, so it's going to take a little while. So I'm going to split this into two videos. The first part will cover resolving the FQDN to the IP address by DNS, and then the second video will cover the HTTP traffic. Okay, so let's walk through how this is going to work right from the start. So again, we're going to use the OSI stack model for this. Don't worry, this is pretty much the last time you'll see it in the course now, but it's really fundamental to networking works, so that's why you've seen it so many times. So one more time, the OSI reference model, we're going to be composing that web traffic and sending it to the web server from our source on the left. So it will compose the packet starting off with the information at the application layer. That will then be encapsulated in the presentation layer header, and then that will be encapsulated in the session layer header. Then we get down to the really important information for networking, so layer 4, the transport layer. This is web traffic, so it's going to be sent with TCP, and the destination port is going to be port 80. Then when the sender on the left is composing this web traffic, it needs to make the layer 3 header next, where it needs to enter the destination IP address, and it doesn't know what the destination IP address is because the user just opened up a browser and entered in their www.flakbox.com. So the sender will need to resolve that to an IP address to complete this packet, and it's going to use DNS for that. So host A, which is at 10.10.10.10/24, wants to send a packet to the FQDN of www.flakbox.com, but it doesn't know the destination IP address. So it will hold on to that packet, and in the meantime, it will send a DNS request to its DNS server at 10.10.100.10. So the host already knows its IP address, its subnet mask, its default gateway, and its DNS server. Host A will compare its IP address and subnet mask to the destination address of the DNS server, and it sees that it's on a different IP subnet, so the DNS request will need to be sent via its default gateway. Host A will hold the DNS request and send a broadcast ARP request for its default gateway, which is at 10.10.10.1. So you can see that in the diagram here. Host A sends an ARP request. It comes from 10.10.10.10. It says it's looking for its default gateway at 10.10.10.1, and it says, hey, what's your MAC address? So that comes from a source MAC of 1.2.3, and it goes to a destination MAC of the layer 2 broadcast address of f.f.f. The ARP request will be received by switch 1 on the left. Switch 1 will add an entry in its MAC address table mapping host A's MAC address of 1.2.3 to port 1. Switch 1 will then flood that broadcast traffic out all ports apart from the one that it was received on. So that will go out port 2. The ARP request is still from 10.10.10.10, looking for 10.10.10.1 with a source MAC of 1.2.3, a destination MAC of f.f.f. That will hit router A's interface of 10.10.10.1. Router A will process the ARP request and see that it is for itself. It will then send a unicast ARP reply back to host A, and router A will add an entry for host A mapping IP address of 10.10.10.10 to the MAC address of 1.2.3, and that will be added to its ARP cache. It will then send the ARP reply. Switch 1 will receive that, and it will add an entry in its MAC address table mapping router A's MAC address of 4.5.6 to port 2. Switch 1 will then send the ARP reply out only port 1, which host A is plugged into, because the ARP reply is a unicast reply and the switch already has host A's MAC address in its MAC address table. It knows it's available out port 1. Okay, so there goes the ARP reply. It says I'm 10.10.10.1 and here's my MAC address. That came from router A. The source MAC is 4.5.6 and the destination MAC is 1.2.3 on host A. Host A will receive that. It will then add an entry for router A, mapping router A's IP address of 10.10.10.1 to the MAC address of 4.5.6. It will add that to its ARP cache, and it will then use that whenever it needs to send traffic to another IP subnet. Host A will then send the DNS request for www.flatbox.com. So that DNS request, it will say, tell me the IP address of www.flatbox.com, please. It comes from a source MAC of 1.2.3 on host A. It goes to host A's default gateway MAC address of 4.5.6. The source IP is 10.10.10.10 on host A, and the destination IP is its DNS server at 10.10.100.10. That is unicast traffic. So switch 1 will send the DNS request out only port 2, which router A is plugged into and which the switch already has in its MAC address table. So the DNS request will come into router A. It will receive the request and see that the destination IP address is 10.10.100.10, the DNS server. Router A has an interface in that subnet of 10.10.100.0/24, so it knows that the destination should be available out that port. It doesn't know the MAC address of 10.10.100.10 yet though, so it will hold the DNS request packet and send an ARP request out of the 10.10.100.1 interface. So there goes the ARP request. That's from 10.10.100.1 on the router. It's looking for 10.10.100.10, asking what its MAC address is. It comes from a source MAC of 8.9.a, which is on that interface on the router. The destination MAC is always the same for an ARP request, f.f.f, the layer 2 broadcast address. The ARP request will be received by switch 3. Switch 3 will add an entry in its MAC address table mapping router A's MAC address 8.9.a to port 1. It will then flood the broadcast traffic out all ports apart from the one it was received on. So that will go down to the DNS server out port 2 as well. Again, the ARP request looks the same. It's from 10.10.100.1, looking for 10.10.100.10 from a source MAC of 8.9.a, destination MAC of f.f.f. So the ARP request hits the DNS server's interface of 10.10.100.10. The DNS server will process the ARP request and see that it is for itself. It will then send a unicast ARP reply back to router A. The DNS server will add an entry for router A, mapping IP address of 10.10.100.1 to MAC address 8.9.a to its ARP cache, and it will use that whenever it needs to send traffic to another IP subnet, because 10.10.100.1 is its default gateway. So there goes the ARP reply from 10.10.100.10 saying here's my MAC address. of source MAC 3.4.5 going back to the router at destination MAC of 8.9.a. Switch 3 will receive that, and it will add an entry in its MAC address table mapping the DNS server's MAC address of 3.4.5 to port 2. It will then send the ARP reply out only port 1, which router A is plugged into, because that is a unicast reply and it already has router A in its MAC address table. So there goes the ARP reply unchanged on its way to router A. Router A will receive that. It will then add an entry for the DNS server mapping IP address of 10.10.100.10 to MAC address 3.4.5 to its ARP cache. Router A will then send the DNS request it was holding from host A to the DNS server. Now, the source and destination MAC address of a packet are updated hop by hop, but the source and destination IP addresses always remain the same, end-to-end, unchanged from the original source to the final destination. The source and destination MAC addresses in our example will be updated to come from router A and go to the DNS server for this DNS request. The source and destination IP addresses are still host A at 10.10.10.10 and the DNS server is the destination at 10.10.100.10. So there goes the DNS request. DNS request is saying, tell me the IP address of www.flatbox.com. The source and destination MAC addresses are now changed to be 8.9.a on router A, going to 3.4.5 on the DNS server. The source IP is still 10.10.10.10 on host A. The destination IP is still 10.10.100.10 on the DNS server. Switch 3 will send out only port 2, which is the DNS server plugged into it, which switch 3 already has in its MAC address table. So the DNS request gets sent down to the DNS server. The DNS server will receive the DNS request packet and see that the destination is itself. So looking at the OSI stack again, it comes in on the physical wire, and the receiver will then process the packet starting at the bottom of the stack, working its way up. So it sees that the destination MAC address is 3.4.5, which is itself. So it will carry on processing the packet. It sees that the destination IP address in the layer 3 header is 10.10.100.10, which again is itself. It will carry on processing the packet. Then in the layer 4 transport header, it sees that it's UDP and it's on port 53, so it knows that this is a DNS request because DNS uses UDP port 53. It will then pass the packet up the rest of the stack, so it'll look at the session header, the presentation header, and the application header, and it will process that DNS request. The server will look in its DNS database and see an address record for www.flatbox.com at 10.10.12.10. That was configured in DNS. It will send that information back to host A in a DNS response. It knows to send the response to 10.10.10.10 because that was the source IP address in the DNS request. And it knows to send it via router A because router A is its default gateway and the destination is in another subnet. The DNS server already has router A's MAC address in its ARP cache, so it does not need to send an ARP request for this. So the DNS reply says that www.flatbox.com is at 10.10.12.10, the source MAC is 3.4.5, the destination MAC is its default gateway at 8.9.a, source IP is the DNS server at 10.10.100.10, and the destination IP is host A at 10.10.10.10. Switch 3 will receive the DNS response and it will send it out only port 1, which router A is plugged into and which it already has in its MAC address table. So it passes that on to router A. Router A will receive the DNS response packet and see that the destination IP address is 10.10.10.10. It has an interface in the subnet of 10.10.10.0/24, so it knows that the destination should be available out that port. And router A already has the MAC address for 10.10.10.10 in its ARP cache. So again, it doesn't need to send another ARP request. So it will send the DNS reply out that interface. Again, it is going from source IP 10.10.100.10, the DNS server, going to destination IP 10.10.10.10, host A. So that doesn't change, but source and destination MAC will be updated. Source MAC is 4.5.6, and the destination MAC is 1.2.3, which is the MAC addresses on the left-hand side of router A. Switch 1 will receive the DNS response and send it out only port 1, which host A is plugged into and which it already has in its MAC address table. So it passes the DNS reply down to host A. Host A now learns from that DNS response that www.flatbox.com is available at 10.10.12.10. It can now update the packet it was waiting to send to www.flatbox.com with that destination IP address. Host A sees that the web server is not on its own subnet, so it knows that any packets it sends there must go via its default gateway. Okay, so at this point, host A has learned the IP address of the web server through DNS. So that covers us for part 1 of this lecture. In part 2, in the next lecture, you'll see how the actual HTTP traffic makes it over to the web server.